Okay, in this video we want to talk about the epsilon delta definition of the limit. So our definition here, we'll write that the limit as x goes to a of f of x equals L, that this means that for any epsilon bigger than 0, there is a number delta bigger than 0 such that 0 less than absolute value of x minus a less than delta implies absolute value of f of x minus L is less than epsilon. So you might think, where is this all coming from? Well, part of this is two numbers are close on the number line if the absolute value of their difference is small. And here typically epsilon is small. We're saying no matter how small epsilon is, but positive, that there's some delta such that x close enough to a, that is within delta of a, but not equal to a. Notice I have bigger than 0 here, so x can't equal a. That this closeness of x to a implies f of x is close to L. So we have to kind of reason this out here and see what's going on with a specific instance. And we can look at a simple example. So let's say I claim the limit as x goes to 1 of 2x plus 3 is 5. Okay, and I'm going to use this definition. So let me get a new page here. So I said the limit as x goes to 1 of 2x plus 3 equals 5. So what do we want? We want our absolute value 2x plus 3 minus 5 to be less than epsilon. We want to find a delta on our x that will make this work. So what I can do here is do some algebra. So I have 2x minus 2 absolute value less than epsilon. 3 minus 5 gives me negative 2. I can take that 2 out of here. Then I could write x minus 1 in absolute value less than epsilon over 2. And each of these steps is reversible, right? So if we let delta be epsilon over 2 here, then our x minus 1 here, bigger than 0, less than delta, implies x minus 1 is less than epsilon over 2. And we can do all these steps in reverse and eventually get absolute value of 2x plus 3 minus 5 is less than epsilon. So that proves that this limit x minus 1, as x goes to 1 of 2x plus 3 equals 5. Graphically, we can think about what's going on here if we graph our function. So we want to draw a little picture here, but here's maybe the line y equals 2x plus 3, and here might be the line y equals 5, and down here we have x is 1. So here's my x-axis, my y-axis, and our function is assigned. What we're saying is that we can make within this band here, so I could have this as y is 5 minus epsilon, and up here have y is 5 plus epsilon, that if I require x close enough to 1 here, my f of x will be between 5 minus epsilon and 5 plus epsilon. So I want my little deltas down here, some interval there, so that when I go up here and I look on my graph, I have this little corresponding line segment. All my points on that little line segment above the one endpoint and the other endpoint. All of those lie in this band here. And what we found here, that delta B, so this is 1 plus delta is 1 plus epsilon over 2. And on this side we had 1 minus delta was 1 minus epsilon over 2. So for whatever epsilon that we have here, we can get a delta here that works, that satisfies that definition. Okay? So that's pretty straightforward. Another example, claim that the limit as x goes to 0 of x squared equals 0. Right? So here we want the abs value of x squared minus 0 here to be less than epsilon. And we're considering x close enough to 0, and I can do a similar thing. Abs value of x squared less than epsilon. So abs value of x less than the square root of epsilon, because that's an increasing function, that this I can go in reverse here. So this is abs value of x minus 0 less than square root of epsilon. So here we let our delta be square root of epsilon. Will do the trick here. Then our x minus 0 less than delta implies x minus 0 less than square root of epsilon. So we do all these in reverse, and we're going to get x squared minus 0 less than epsilon. So this was another easy example. Now in practice, you don't normally do the delta epsilon proofs of these things. You use something called limit laws to prove these limits. But this is just to illustrate what's going on with our limit. And for that one too, we can think graphically. If we like, we can draw this. Here's my function y equals x squared, and we want to show limit as x goes to 0 of x squared equals 0. That was our thing here. So this would be y equals 0 plus epsilon and y equals 0 minus epsilon. And so it turns out if we were in this band here, so here's our 0 plus delta, here's our 0 minus delta, that now all of the points on my curve here, that little piece of the function, lie within this band. So these are limits that existed, but you can't always get that. Some limits fail to exist. I claim, for example, the limit as x goes to 0 of sine of 1 over x does not exist. Okay? And basically, if you try to graph this, what's going on here, you're oscillating. So here would be the horizontal line y equals 1, and down here the horizontal line y equals negative 1. So you have to use your imagination here. And my sine function, as I come in here, of 1 over x, I'm going to oscillate between these bounds. And as I come in, I oscillate more and more, and likewise over here. So you would use a computer or something to generate this, but we can show here that no matter how close we are to 0 here, so my origin here, I'm coming in, so how close I am to the origin there, that there's points that on our function where we're up here at 1 and points down here where we're down at negative 1. No matter what small band we take, we can't get a single number here. And yeah, if we wanted to prove this rigorously, we can. You can just note here, if you like, that the sine of pi over 2 plus 2 pi n is 1 for our capital N here being 1, 2, 3, 4, etc., because it's periodic. And so here, if I let my x sub I be 1 over pi over 2 plus 2 pi n, then my f of x sub I here is 1. But see, what's going on here is that I can make my x sub I arbitrarily small here by requiring n large enough. And also, if I want, I can note that the sign of 3 pi over 2 plus 2 pi n is going to be negative 1. My n is 1, 2, 3. So here, if I let my xi tilde be 1 over 3 pi over 2 plus 2 pi n, my function at these numbers here is going to be down at negative 1. So I have these numbers that are close to 0 but give me negative 1, and these ones here that give me positive 1. So there's no chance of this to come at some limit. If you look at the previous example that we had here, was that as we get closer and closer to 1 here, our y values got closer and closer to 5, a single number. But in this example, no matter how close I'm to 0, there's some points up here and some points down there. So we can show that the limit there just does not exist.